So I mentioned on the previous page that the first two of these three conditions can be expressible in terms of the determinants of the underlying matrices A and B. So in the case of the first one, the determinant of k times A is given by this rule down here. It's equal to k to the power of n times the determinant of the matrix A, where n is just the number of rows and columns of the matrix A. But now we'll take a look at this second one, the determinant of the product AB. And it turns out this rule is as nice as you could possibly hope for. If you have two n by n matrices A and B, you could say the following: the determinant of the product AB is actually exactly equal to the product of determinants of A and B considered separately. So this is what you can write: the determinant of AB is equal to the determinant of A times the determinant of B. So that is a rule that tells you how determinants behave over products. I'm not going to prove this to you in detail. We're just going to look at how to apply it in general, and that's what you'll see on the exercise sets. But this is actually worth appreciating. I think I would say this is not obvious at all. That part is worth mentioning. Consider how complicated matrix products are just to compute a single entry. Think about that for a moment. And then also consider how computationally demanding determinants are. And when you put those two ideas together, it's almost a bit miraculous that this works out so nicely. So let's test it. Let's just test it in a simple case of two 2x2 matrices. Now, please don't confuse this with a proof. This is not a proof of this property. All it is that we're just checking that it works in this particular case. But this is a rule that holds in general for any two square matrices A and B, as long as you can multiply them, right? They have to be of the same size so that this product makes sense. But this is true in general. But let's just check it in the case of this example down here. So I've got a 2x2 matrix A and a 2x2 matrix B. Let's start by taking the determinants of the two individual matrices, and we'll compute the right-hand side of this equation. So, well, the determinant of A, well, I'm going to go 3 times 1 minus 1 times 2. So I'll get 3 minus 2, which is equal to 1. Now if I compute the determinant of B, well, it's a 2x2 matrix again, so I'll go negative 1 times 8, which will give me negative 8, minus 3 times 5, which is 15. So you're going to get negative 23. Well, if I multiply those two results, determinant of A times the determinant of B, I'm going to get negative 1 times, or pardon me, 1 times negative 23. So I'll have 1 times negative 23, which is equal to negative 23. Okay, so let's keep that in mind. And now let's compute the product of AB, the product AB. And so we can do that here. There's room up here. We can write down the product matrix, A times B. So it's a 2x2 multiplied by a 2x2. The result is also going to be a 2x2. So to compute the first entry in the first row, we're going to take row 1 from A and column 1 from B. So 3 times negative 1 plus 1 times 5. That'll be negative 3 plus 5, which is 2. Now the second entry in the first column, this one down here, we're going to take the second row of A in the first column of B. So 2 times negative 1. And 1 times 5, that's negative 2 plus 5, which is positive 3. Now what about this entry up here? So we'll have the first row from A and the second column from B. So you have 3 times 3 plus 1 times 8. That's going to be 9 plus 8, right, which is 17. And then our bottom right entry of 2 times 3 plus 1 times 8, that's going to be 6 plus 8, which is 14. Okay, so that's our product, AB. Let's compute the determinant of that product directly. All right, so what would we get? Well, do the 2x2 formula. 2 times 14 minus 17 times 3. And if you work these out, you're going to get 28 minus 51, which ends up being exactly equal to negative 23. So in this case, they're equal, right? So we can say that here. Therefore, in this case, the determinant of AB is equal to the determinant of A times the determinant of B, right? So therefore, it works in this particular case. Now, just to reiterate, I'm promising you, even though I'm not proving it to you in general, this holds in general. So let's just clarify. This holds in general. So in other words, for any square matrices A and B, such that this product is defined, you have this rule and you can trust it. Okay, and one nice consequence of this is it allows you to get a good idea about the following. So before I say too much, let's just go through this carefully. So we're going to look at a special case of dealing with invertible matrices. Now I've kind of hinted about this vaguely in the past, earlier in chapter 2, but if you missed it, I wouldn't blame you because I didn't mention it very much and I didn't emphasize it yet, but that's going to change now. There's a real reason that we study determinants. And in the case of 2 by 2 matrices, we've already seen, based on how we define 2 by 2 determinants, that the determinant of a 2 by 2 matrix is equal to 0 if and only if that matrix is not invertible. Or in other words, the determinant of invertible matrices is always non-zero. So we're going to look a little bit at why that's true, and we're going to state it once and for all for general square matrices. And that's what's really interesting about determinants, and that's our main application that we're going to look at. So let's just start by making an observation. Let's say you have an invertible matrix A. So we're not going to make any assumptions about the matrix A other than that it is invertible. Well, if it's invertible, then by definition of its inverse, A times A inverse is going to give you the identity. Right? That's for sure. So what we're going to do is just take the determinant of both sides of this equation. So what that's going to give you is the following. The determinant of A times A inverse is equal to the determinant of the identity. Right? I just did exactly what I said I would do. Take the determinant of both sides of the equation. But now we're going to apply this rule up here, that the determinant of a product of 2 matrices is equal to the product of the determinants of the 2 factors. So if you apply that down here on the left-hand side of this equation, we get the following. So I'm going to say which implies that the determinant of A times the determinant of A inverse is equal to what? Well, the determinant of the identity. This is actually something you can, I've mentioned this once before, but I'll go through it again in detail because it's easy to forget. The determinant of the identity, well, the identity is a diagonal matrix, which in particular is an upper and lower triangular matrix, but all that matters is that it's an upper triangular matrix, because the determinant of an upper triangular matrix is the product of the entries along the main diagonal. But all the entries on the main diagonal of the identity are equal to 1, which means that its determinant is the product of a whole bunch of numbers that are all equal to 1. So it's just going to be 1. So the right-hand side of this equation is equal to 1. Now what is the point of this? Well, there's a couple things you can get from here, but the first observation you can make is that the determinant of A is not equal to 0. It cannot be equal to 0. It could be anything at this stage, since we don't know what the matrix A is. It could be absolutely anything except the number 0. And why can't it be 0? Well, if it were 0, how could this product give you 1? If this were equal to 0, then the determinant of A inverse, it wouldn't matter what it is. If you multiply it by 0, you're not going to get 1. You're going to get 0. So that's why you can say that the determinant of A is not 0. So this cannot be 0. Okay, and that's our first observation. And well, the second thing you can get from this is what's going to happen now if you divided A inverse over to the other side of, or pardon me, if you divided the determinant of A over to the other side of the equation, you get a formula for the determinant of A inverse. So that's actually, this is a partial justification of the theorem that I'm going to state below. And as with the rule up top, as with the rule up here, I'm not going to prove this to you completely, but just the observation we did at the beginning is at least a partial justification. So let's finish this statement, or both of these statements. So if you have any n by n matrix A, you can say the following. A is invertible if and only if its determinant is not 0. And that's a very powerful application of determinants, and it's very useful for theoretical purposes, because often when you're working abstractly with matrices, you don't actually need to get your hands on the inverse. You just need to know if one exists. And for that purpose, it's often way easier to compute the determinant of the matrix to check whether it has an inverse than it is to actually try to work out what the inverse is, especially if you're working with a matrix whose entries you don't know. If you don't know all the entries, you can't compute the inverse. But you might be able to compute the determinant. And so that's one of the reasons that the first statement is very powerful, and it is our primary application of determinants. For part 2, the second statement says that if A is invertible, then, well, just what we set up here, right? If you take the determinant of A and you divide it over to the other side, then you get the following. You get the determinant of A inverse is equal to 1 over the determinant of A. And since that's a formula, I'm going to put a box around that one because that's a good one to remember. So if you are making a formula sheet, you might want to add this one along with this property and as well as this property up here. Okay, so let's look at an example of applying this theorem. In particular, we'll apply the first statement, which says that a matrix A is invertible if and only if its determinant is non-zero. So here we've got an example, and we're given a 3×3 matrix, and we're asked to determine if it is invertible or not, right? If it's invertible, justify it, and if it's not invertible, then say so, but also justify it. So that's how you should interpret a question like this. So how are we going to do it? Well, based on the theorem above, all we need to do is check if its determinant is equal to 0 or not. So it just comes down to computing the determinant of this 3×3 matrix. So let's go ahead and do that. The determinant of A, and I'll just shift to my bar notation. So 2, 5, 5, -1, -1, 0, and 2, 4, 2. So we have to, well, there's several ways to compute the determinant here. I'm just going to do cofactor expansion, and I'm going to choose the second row to do cofactor expansion because it's got a 0. I could have also chosen the third column, and that would have worked as well, but I'm going to do the second row. So the sign position of this entry, the sign of this entry, or this position, is a negative, right? If I start at the top left corner and go positive, negative, positive, negative, that's how I can work out the signs in this row. So I'm going to have negative, -1 times this 2×2 determinant given by 5, 5, 4, 2. Then I'll have, for the next term, will be positive because I alternate. Then the entry is -1, and the 2×2 determinant here is going to be, well, we got this -1 is the entry in the middle. So if I delete this row and this column, I'm going to have 2, 5, 2, 2. And that's what I get if I do cofactor expansion. Okay, so let's go ahead and work this out. So we've got 5 times 2, which is 10, minus 5 times 4, which is 20. So you've got 10 minus 20, which is going to be -10. And over here, we've got 2 times 2, which is 4, minus 5 times 2, which is 10. So over here, we've got 4 minus 10, that's going to give us -6. So what do we get in the end? We get, this is -1. This is all just the same as +1, right? So this whole first term is just +1 times -10. So we're going to get -10 for the first term. And then the second term, we've got -1 times -6. So that's going to be -10 plus 6, right? Which is -4. And we actually didn't really care about the exact number. The only thing we really cared about is whether or not this determinant works out to 0. But it didn't. It gave us -4. So by the first statement in theorem 1, our determinant is not 0, which means the matrix A is invertible. So that's how we can do this. So therefore, let's be complete here. Let's say, therefore, since the determinant of A is not equal to 0, A is invertible. And then since we were asked to determine whether this matrix was invertible or not, let's put a box around that portion of our answer because that's pretty important. And so that's how you can use determinants to find out whether a matrix is invertible or not.